Okay, in this example, we're going to look at an interesting physical phenomenon that is sometimes associated with the gravitational slingshot. Because basically, we're going to see that our baseball here, dropped on top of a bouncing basketball, is able to get bounced to a much higher height than it started at. All right, so we're going to see how that is possible. All right, so let's read over the problem and think of our key equations. So we have a small ball of mass m, we're actually going to find that mass, that is aligned above a large ball, so in other words it's directly above, and their centers of mass are lined up. That larger ball has a mass of 0.63 kilograms. There's a slight separation between the two, as shown in the figure. So the two balls are dropped simultaneously from a height of 1.8 meters. And we're going to assume that the radius of each ball is negligible. That's not a very good assumption considering it's only 1.8 meters and basketballs are a few centimeters wide, but good enough for this problem. So in part A, we're asked if the larger ball rebounds elastically from the floor and then the small ball rebounds elastically from the larger ball, what value of m results in the larger ball stopping when it collides? Okay, so we're going to have a collision between the downward moving baseball and the upward moving basketball. All right, so let's think about what we need here then. So we're going to need kinematics during the free fall. Okay, we're going to have conservation of momentum in the y direction for the upward moving basketball and downward moving baseball. All right, and also we're going to have conservation of energy during the collision, and so that's going to be E1 equals, let's see, we'll call it E and E prime to be consistent with our notation. Oh, that would be a prime there as well. So E prime during the collision, during the elastic collision, because it's a fully elastic collision, so energy is conserved. Okay. And then for part B, we're going then to also use the conservation of energy to find the maximum height. Okay, and actually, so call that E1. Sure. So E1 equals E2 to find maximum height. And certainly for step one, we could use conservation of energy for the free fall to find the velocity, but let's just do a review here and do kinematics, so we can do that to find the velocity when they hit the ground. Okay, which of course will be independent of the mass, so they're both going to be traveling the same speed at the moment of the collision, but in opposite directions. Okay. So let's go ahead and take a look at how fast the balls are going when they hit the ground. Okay, so we're going to have V equals V naught plus AYT. All right, that's going to become not 0, but V equals 0. And then, oh, actually, I want to use the one for displacement because we don't want to have to find the time it falls. So we're going to use v squared plus v naught squared plus 2 alpha delta y. Okay? And so what that's going to look like is v squared is going to be equal to 0 squared. All right? And then plus 2 times negative 9.8 meters per second squared times 1.8 meters. Okay, so then if we want to find the velocity at the ground, the moment of the ground, it's just going to be the square root of, well, 2 2gy, right? 2gy. All right. And it's going to be in the negative direction. All right, so we have, okay, it's because, let's see, if we want to find, let's see here, okay, but so we don't end up with a negative inside the square root, we should also acknowledge that the y, so sticking with the coordinate system we have, which is positive y facing upwards, by the way, right, there's our positive y, that this would be, we'd have our initial position being 1.8 meters, and our final position being 0. So it'd be 0 minus 1.8, which gives us a negative in there. All right. So, and anyway, this has the form of 2gy, which is exactly what we get from conservation of energy because kinematics and energy are consistent with each other. And so then we can go ahead and just leave that as our velocity. Okay. So the velocity of the basketball, which I'm going to call big M. So let's go ahead and label these. All right, so this one here is going to be big M. All right, let's put that off where we can see it, or actually let's put it in color we can see. All right, so big M. All right, and then we're going to have little m right here. Okay, so little m and big M. All right. Okay, so V for big M is going to be positive 2gy because it's traveling upwards. Okay, V for little m is going to be negative 2gy because it's still on its downward motion by the time the collision happens. Okay, and these are going to be the velocities that we're going to use for the initial velocities for conservation of momentum, which now we're going to move on to. All right, so let's consider our momentum. So Py equals Py final. Well, that's going to become, okay, so we're going to have little m times negative 2gy, all right, and then plus big M times positive 2gy, okay, and that's going to equal little m times v little m final plus big M times v big M final. Okay, so those are our two unknowns that we're going to have to solve for. All right. Okay, so that means we're going to need a separate equation to help us solve for it. And that equation is going to be our energy equation, which is going to be E equals E prime. Okay, and we're going to show the energy equation in head-on one-dimensional elastic collision form. And it wouldn't make sense to talk about a conservation of energy for any other type of collision other than an elastic collision. But what that looks like, the conservation of energy equation, is it would be V little m minus V big M equals negative V little m prime minus V big M prime. Okay? So that's conservation of energy. Now we can do the algebra and then solve for what we need, but we have some pre-made equations exactly that have already been done for us. So using our two equations here, energy and momentum, we're going to be able to get right here. So those two equations gives us these two equations, which gives us the final velocity for A and B, A being little m, B being big M, and it will give us the necessary final velocities. Okay, so let's then, right, if we're treating B as, so we'll say, I'll note that here. So note that B is big M and A is little m. Okay, so with that in mind, we can then say, okay, well we want, and the criteria for part A, we want that the larger ball rebounds elastically from the floor, and then the smaller ball rebounds elastically from the larger ball. And we're asked for the value of little m that results in the larger ball stopping after the collision. Okay, well, the larger ball coming to rest after the collision is going to look like v prime b, or vb prime, being 0. Okay, so we need to set that equation to 0. All right, so we're going to have a 0 right here. Okay, and then this is going to be 2 little m over little m plus big M. All right, and then VA, okay, well, that's going to be, VA is little m, so that's negative square root of 2gy, okay, and then plus, okay, and then we're going to have big M minus little m, all divided by their sum again, right, sum in each of the denominators, okay, and then the initial velocity of the basketball, of big M, which is positive 2gy. Okay. Well, our two terms here on the right-hand side of the equation are like terms, so they're going to simplify into 0 just equals big M minus 3m, because we had 2m minus, or negative 2m minus another m, for a total of negative 3m. And, okay, and so then in our denominator, we're going to have the sum of the masses, so big M plus little m. Okay, and then times 2gy. Okay, well, the only way for this to be true, to actually equal 0, is for m minus 3m to be 0, because we're not going to get a 0 out of the denominator. This sort of coefficient of the square root of 2gy isn't going to give us, isn't going to affect our 0. All right, so we can say, thus, for VB prime, and V big M prime to equal 0, we have M big M minus 3 little m equals 0, which is to say that little m is just 1/3 of big M. Nice, clean result. 1/3 big M. Okay, so let's go ahead and just actually do a calculation here. All right, so we were told that it was 0.63, so we're just going to take 0.63 and divide it by 3. All right, so 0.63 divided by 3. Okay, so that's 0.21 for the mass of our baseball. 0.21 kilograms. All right, and that is the answer to part A. Okay, and well, for part B, quite appropriately, we're going to use the other of our prefab formulas here. And again, these formulas, they're quite convenient, but they just come from conservation of momentum and conservation of energy. But they only work for one-dimensional or head-on collisions. Okay, so what that's going to look like is we want to find Vm prime, because if we can find Vm prime, then we can find the height to which the baseball goes. And to remind us what it asks for in part B, it just asks for what height does the small ball reach. All right, because once we have Vm prime, we can find the kinetic energy of the baseball after the collision, and then just find out how, when we convert that kinetic energy to potential energy, the final height. Okay, so let's use our equation here. So Vm prime is going to be big M minus little m, which is 1/3 of big M. Okay, so notice I'm just using the information that we already have here. And then big M plus 1/3 of little m. Okay, and then that's going to be multiplied by VA. Okay, so that's going to be negative 2gy. Okay, and then plus 2 big M. Okay, and then all divided by just the sum, big M plus 1/3 big M. All right, and then multiplied by the square root, positive square root of 2gy. All right, 2gy. So probably the first thing to take note of here is that all our big M's now cancel because we just had that one mass because of the substitution we made. We found out that little m is 1/3 of big M. And we just want then to basically sum up our values here. So on the first term, we have a 1 minus 1/3, so 2/3 divided by 4/3. Okay, so let's just write this out. Okay, so this is going to be 2/3 divided by 4/3. Okay, and in fact, actually, let's go ahead and factor out our common term of the square root of 2gy. Okay, and then we'll do this first one here, but it means we need a leading negative, right? And then plus, okay, well then this other one is just going to be 2, and then over 4/3 again, okay? So if we go ahead and put that in the calculator, we have negative 2 divided by 3, all right, and then divided by 4 divided by 3 plus 2 divided by 4 divided by 3, or divided by 4/3. All right. Okay. All right. So that gives us a value of 1. So let's check that. I think there's a typo here or a small mistake. I see what I did wrong here. So here in the first term was my mistake because A corresponds to little m, right? So this should have been 1/3 big M, and then minus big M like that, okay? So that's actually going to give us, so 1/3 minus 1 is negative 2/3. So that gives us that negative. We'd have the negative there and a negative, second negative, so negative here, or rather, we have a negative from this term and a negative from that term. And so that means that this one becomes plus. All right, so we can go ahead and fix that. All right, just misread the formula. All right. And sure enough, that gives us 2. Okay, so that gives us that our final velocity of the smaller ball, the baseball, is twice the velocity of when it hit the ground. You know, that's quite interesting, okay? So that gives us that Vm prime is just going to be 2 times 2gy. Okay, so then finally using conservation of energy, we're then going to have 1/2 little m times 2 times 2gy squared, because that's just our final velocity, which is our initial kinetic energy, is going to equal mg, and we'll call this h final, for the final height that little m reaches. Okay, so we'll have some more cancellation here. Little m's going to cancel out. Okay. Of course, you know, we know what it was. It was necessary to find that it was 1/3 of m. It only works if it was 1/3 of m. But it's going to cancel out for energy. So then let's go ahead and solve for h final. All right. So h final, the final height of little m, is going to be, well, I just realized our 1/2 and our 2 cancel as well. So it's just going to be, well, 2gy and then divided by g, right? So if you look at this, it's 2gy divided by g. So our g's cancel, okay? So it's just 2y. Okay? Well, our original release height was 1.8 meters. That's the value that I used for y. Okay, 1.8. And I never plugged in I mean, we could have, done this numerically, right? We could have, had a number here rather than just an expression. But of course, we wouldn't see the dependence, right? If we had plugged it in, we might think, oh, it depends on how high it's dropped. But we're seeing here that it's actually always just going to be twice the dropped height. So, it doesn't matter. In particular, that was 1.8 meters, other than the fact that our final result is 3.6. Okay? Let's see, and oh, nope, I made a mistake. It's a small one, but we can easily fix it. Okay, so this 2 doesn't quite cancel, right? Because what's going to happen is this is going to become 2 squared. So I can do this here. I'll put the square root there, and so this is going to become 4. So when I cancel with the 2, it's left as a 2, which means that we're going to have 2 here. Okay, so our h final is going to be 4, right? Because we had, yep, exactly. So it's 4gy. So then it's 4y. So then our final height is just 1.8 times 4, which I will check on the calculator. All right, so 7.2 meters. Okay, respectable height, only dropping it from, about 6 feet above the ground. This thing is going to shoot up in the air to a, over 20 feet in the air. So pretty neat. Okay, so we saw here using conservation of energy or conservation of momentum and a collision between unequal masses, we can get a high launch. All right, thank you.